In 1935, Einstein, along with Podolsky and Rosen, published one of the most thought-provoking papers in the history of physics, now famously known as EPR paper. In it, they raised a profound question: is quantum mechanics a complete description of physical reality? At the heart of this question lies a striking and counterintuitive idea: two particles, once interacted, can remain deeply connected no matter how far apart they are. A measurement performed on one seems to instantaneously influence the other, a phenomenon that Einstein famously referred as spooky action at a distance. In this video, we shall carefully unpack this remarkable paper, not just conceptually, but mathematically. We will follow the original arguments presented by Einstein, Podolsky, and Rosen, examine the assumptions they made about reality and locality, and explore how the reasoning leads to fundamental paradox. As we progress, I'll guide you through the mathematical structure underlying the argument, helping you see how the paradox emerges naturally from the formalism of quantum mechanics. By the end, you will not only understand the essence of EPR paradox, but also appreciate why it continues to shape modern physics, from foundational debates to cutting edge development in quantum information and computing. Let us begin this journey into one of the most deepest questions ever posed about nature of reality. In the description box, you can find a link for the PDF of the paper. I am Dr. Shyamkant Anwane, Professor and Head Department of Physics, Sri Shivaji Education Society, Amravati Science College, Nagpur. So let us begin our journey. For learning EPR paradox, we shall refer nothing other than the Einstein-Podolsky-Rosen's paper, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? In a complete theory, there is an element corresponding to each element of reality. A sufficient condition for the reality of physical quantity is the possibility of predicting it with certainty without disturbing the system. In quantum mechanics, in case of two physical quantities described by non-commuting operators, the knowledge of one precludes knowledge of the other. Then we have two options: either one, the description of reality given by the wave function in quantum mechanics is not complete, or second, these two quantities cannot have simultaneous reality. Consideration of the problem of making predictions concerning a system on the basis of measurements made on another system that has previously interacted with it leads to the result that if one is false, then 2 is also false. One is thus led to conclude that the description of reality as given by a wave function is not complete. This was the abstract of the paper I was reading. Now, step by step, we shall consider the contents of the paper for discussion. The first point I want to raise is description of reality in quantum mechanics by a wave function is not complete. This, in short, I shall be calling quantum mechanics is incomplete. That is our statement number one. Similarly, the second statement is that two quantities, conjugate variables I am talking about, cannot have simultaneous reality. This term, in short, I shall be calling the reality is limited. Now, the first statement, quantum mechanics is incomplete, is written as 1, and negation of one I shall be calling as quantum mechanics is complete. On contrary, second statement is reality is limited and negation of two is reality is not limited. So conjugate variables in Heisenberg's uncertainty principle, the two quantities like position and momentum, energy and time are called conjugate variables. Conjugate variables are pair of physical quantities that are mathematically related in such a way that they cannot be simultaneously measured with arbitrary precision. For example, position x and momentum p cannot be measured simultaneously accurately. Similarly, energy and time, angular position and angular momentum cannot be measured simultaneously. A syllogism is basically a logical shortcut to reach to conclusion from known facts. A syllogism is a form of logical reasoning in which conclusion is drawn from two statements, as we are talking about statement 1, statement 2, negation of A, negation of 2. I mean negation of 1, negation of 2. Syllogism is a deductive argument consisting of major premise, that is general statement, and minor premise, that is a specific statement. On the basis of this, we attempt logical conclusion. Major premise, for example, all humans are mortal. Minor premise is Socrates is a human. Conclusion, therefore, Socrates is mortal. The key idea here of using syllogism is if the premises are true and the structure is valid, the conclusion must also be true. There are different kinds of syllogisms. Categorical syllogisms, most common uses all and some terms. Hypothetical syllogism, if and then statements. Disjunctive syllogism, either or statements. Now we have quantum mechanics. The question is whether it is incomplete or complete. If it is complete, part 1 and part 2 we are going to talk about. Part 1 is referring to Heisenberg's uncertainty principle, and in part 2 we are going to consider a thought experiment. Non-commuting observers can't be simultaneously real. Look at this statement. Non-commuting observers can't be simultaneously real. Like position and momentum, we cannot simultaneously measure precisely, that is our Heisenberg's uncertainty principle. And in the second part, the thought experiment we are talking about will be dealing with non-commuting observers can be simultaneously real. We shall focus on this angle. And here we shall be talking about statement 1 and negation of 1. So here you can observe this is statement 1 is quantum mechanics is incomplete, and negation of that is quantum mechanics is complete. This leads to second statement, that Heisenberg's uncertainty principle, that is non-commuting observers can't be simultaneously real, and negation of that is non-commuting observers can be simultaneously real. So we have two options, either 1 or 2. Negation of 1 implies 2, and negation of 1 implies negation of 2. So negation of 1 can never be leading us to statement 2, and negation of 2. This is a kind of contradiction. Both statement 2 and its negation cannot be derived from 1. Now the local causality, or simply we can call sometime as locality or local realism. Local causality is the principle in physics stating that an object can be influenced only by its immediate surrounding, and any cause effect influence cannot travel faster than the speed of light. It combines two ideas, locality and causality. Locality means no instantaneous influence at a distance, and causality, we are saying it in a sense, causes precede effect in time. This idea is a central idea in the theory of relativity and was strongly emphasized by Albert Einstein. So an object can be influenced only by its immediate surroundings, and any cause-effect influence cannot travel faster than light. We have many such examples in our day-to-day life, billiard balls hit by others. So there is a cause and effect in fields, force at a distance, say gravity, radio waves, magnets. These are the examples which are causing field, and we have some effects which are occurring because of the presence of the field. Local dynamics mediated by some field. Illustration of local causality through a boat in water. You can consider an example that uh, there's a boat in water and some wave is traveling. It will travel with definite speed and it will reach to the boat and the boat will shake. A famous illustration of causality in the principle in the field of special relativity under the subject physics is the grandfather paradox. You can consider for your reference. Einstein believed in local causality, and so his theories are also following local causality. Shockingly, quantum mechanics exhibits non-local phenomena. So for exploration, you can pick up some events in your day-to-day life. If something happens at a point A, it can affect point B only after some time, and the signal must travel through the space, obviously not instantaneously. In everyday examples, you can consider light signal. If you switch on the bulb, the light reaches your eyes almost instantly, but still at a finite speed, that is speed of light. Effect, I mean seeing light, follows cause, which is switching it on. Sound propagation, you clap your hands, a person far away hears sound after a delay. That we really understand very nicely nowadays with the scientific background that we have from our school science itself. Effect travels through air not instantly. Domino effect, you push first domino, each domino falls one after another. The effect propagates step by step locally. Gravitational influence, if sun suddenly disappears, Hermann Bonde's thought experiment, if sun suddenly disappears, hypothetically, earth would continue orbit for about 8 minutes, time taken by light to travel from sun to earth. Gravity changes propagates at finite speed, not more than speed of light. So there will be a lag of 8 minutes. In quantum mechanics, things are a bit different. I mean, contrast with quantum mechanics as regard to the local causality. In quantum physics, especially the EPR paradox, which we are going to learn, two entangled particles seem to affect each other instantaneously even when they are far apart. They're not in same light cone. This appears to violate local causality, leading to Einstein call it spooky action at a distance. So in all, I want to summarize this slide by saying that no faster than light influence affects, rather, no faster than light influence effect follows causes through space and time works perfectly in classical physics and relativity, but challenged by quantum entanglement. So when a boat moves through water, it generates ripple that propagates outward as waves. These ripples travel through the medium and can disturb the objects at a distance. Similarly, the presence of the boat affects us through physical interactions, light waves, sound waves, and water ripples. Light waves reflected from the boat reach to our eye, enabling us to see it, whereas the sound waves are produced by the boat travel through air and vibrate our eardrums, allowing us to hear. Water ripples created by the boat can physically shake the nearby objects in the water or even a person through direct contact within the water. In all these cases, the influence of the boat is transmitted through the medium via waves or signals. Importantly, no effect occurs instantaneously. Every cause is propagated at a finite speed. The ultimate speed limit for any cause-effect relation in the nature is the speed of light, which ensures that the interaction remains local and do not occur instantaneously across the space. So everyone who has dealt with Heisenberg's uncertainty principle is quite familiar. I mean, those who have worked with quantum mechanics, they are already familiar with Heisenberg's uncertainty principle. And there we are talking about position and momentum in terms of operator. And we already know that a particle's position and momentum can't be known precisely simultaneously. Let us take up this warm-up example wherein position and momentum, position x and momentum px, do not commute. So here I am using the operator notation. This x with a hat and p with a hat is operation of position operator and momentum operator on the wave function, and then we are making momentum operator first and then position operator. This is not equal. It means that they do not commute. So here this mathematical notation for this operation, x cap x hat comma p hat in the square bracket means x hat p hat minus p hat x hat. It's not zero, incidentally. So here x hat has value x and p hat has value minus ih cross del del x. It means that when you operate this operator, it yields position. When you operate this operator p hat, it offers momentum, and mathematical representation of this momentum operator is like this minus ih cross into partial derivative with respect to x. Now this is in sequence operated on psi. It will offer you this quantity on right hand side, and reverse order operated on psi will offer this. Is it equal? No, it's not equal. Thus, square bracket x hat p hat is not equal to 0, rather it is equal to ih cross psi. So we conclude that they do not commute, and the Heisenberg's uncertainty principle in most generalized representation of two quantities which are coupled as position and momentum, energy and time, uh, angular momentum and angular position, so on. So delta A, that is uncertainty in the measurement of A into uncertainty in the measurement of B, is always greater than or equal to what you call absolute value of expectation value of commutator of operator A and B is h cross by 2. It is always greater than or equal to h cross by 2. In real world, this value of h cross is very small. Here you can observe it is 0.5 into 10 power minus 34 joule second. Now the question is that whether quantum mechanics has a limitation or the blurriness of reality. I mean to say that if you try to measure position and momentum simultaneously accurately, your accuracy cannot be beyond h cross by 2. Why it is so? Whether quantum mechanics is limited or incomplete or insufficient, or the reality itself is blurry. That's a question. Now let us talk something about theory and reality. Understand the distinction between reality, which is independent of theory. For success of theory, there are questions. Is the theory correct? Means perform an experiment and verify it with the theory and check whether it agrees or not. Is the description given by the theory is complete? Yes or no? You have to judge. In 1935, Einstein, Podolsky and Rosen asked a question on the completeness of the theory, not correctness of the theory. In science, a theory is judged not only by whether it is correct, but also whether it is complete. Correctness means, does it have right predictions? If yes, then it is correct. Completeness means, does it describe all aspects of reality? It depends on the answer whether it is complete or not. So, what is correctness? A theory is correct if its predictions match with the experimental result. It is consistent with the observations. For example, Newton's law of gravitation correctly predicts motion of planets, falling of object. Hence, it is correct within its domain. Then the question comes, what is about completeness? A theory is complete if it explains all physical phenomenon in its domain. No additional hidden variables, unknown factors are required. Consider the case of quantum mechanics and say relativistic quantum mechanics. The relativistic quantum mechanics is capable of offering extremely correct results. It predicts atomic spectra. We can talk about semiconductor theory, laser theory, so on and so forth. But the question is quantum mechanics complete? The famous debate on EPR paradox, Einstein argued that quantum mechanics is not complete. There must be hidden variable. His famous concern is known to us through this paper which we are discussing in this present lecture. God does not play dice. A powerful way to understand the relationship between theory and reality is through the example of contours of mountain versus the real mountain itself. The real mountain, that is a reality. The real mountain is a physical, complex, three-dimensional structure. It has irregular slopes, rocks, vegetation, and varying textures. Changing weather conditions like wind, snow, erosion causes changes. Countless fine details cannot be fully captured. In short, the real mountain is a rich, dynamic, and infinitely detailed. It represents reality in its full complexity. Contour map theory. A contour map is a simplified representation of the mountain. It uses lines to connect points of equal heights called contours. It reduces 3D object into 2D abstraction. It captures essential features like elevation, slope, and shape. This is analogous to scientific theory. It does not reproduce reality in full detail. It highlights key features relevant to understanding and prediction. It is constructed using assumptions, approximations, and mathematical tools. Now we shall talk about the condition of completeness. A physical theory is said to be complete if every element of physical reality has a corresponding representation in the theory. For example, we have mass of the particle. In theory, we represent it by m. We have momentum of particle, which is mass into velocity, and in theory we have p representation for that. So on and so forth. It means that we have every element of physical reality that has corresponding representation in the theory. That is the meaning. An element of reality is the quantity whose value can be predicted with certainty without disturbing the system. This is important. Without disturbing the system, the element of reality is a quantity whose value can be predicted with certainty. If such elements exist but are not described by the theory, then that theory is incomplete. So, the condition of completeness, I hope you have understood that every element of physical reality must have a counterpart in the physical theory. The element of physical reality according to EPR. If we can predict the value of physical quantity with certainty, that is probability 1, without disturbing the system, then that quantity corresponds to an element of reality. For completeness requirement, for the theory to be complete, all such elements of reality must be fully described within the theory. Meaning thereby no hidden variables, no missing information, no unexplained correlations. The implication of completeness in quantum mechanics we shall discuss in the light of EPR argument. We can predict position or momentum of a distant particle without disturbing it. Hence, both should be the element of reality. But in quantum mechanics, we cannot assign definite value to both simultaneously due to uncertainty principle. Therefore, EPR concludes quantum mechanics is incomplete. That we are going to prove at the end, but I have exercised the implication of completeness on quantum mechanics. So in one line, completeness means one-to-one correspondence between physical reality and theoretical description. That's it. Consider a source S that emits two particles A and B. They are entangled. Their properties are strongly correlated. They have a spatial separation, space separation. The particles move apart, could be in light years apart. No physical interaction between them afterwards. The measurement at A. If an observer measures either position of particle A, instantly knows position of B, and if the observer measures momentum of particle A, instantly knows momentum of particle B. The key observations are that this prediction of B is certain with probability 1 without disturbing B. Hence, according to EPR, both position and momentum are elements of reality. The paradox is that quantum mechanics says that we cannot know position and momentum simultaneously, but EPR says that both must be real, predictable, without disturbance. The contradiction here is quantum mechanics is incomplete as EPR claims. The measurement at A seems to instantly define reality there at B, violating classical locality. Eigenfunction. The wave function psi is an eigenfunction of an operator A cap. If A cap psi is equal to small a psi, where small a is a number, then the physical quantity A, capital A, has with certainty the value small a whenever the particle is in the state given by the wave function psi. In accordance with this, the reality or the criterion of reality for a particle in the state psi is described or say abided by this equation: a cap psi is equal to small a psi. There is an element of physical reality corresponding to physical quantity A. For example, psi is a wave function expressed by e to the power I p0 x upon h cross. Here, p0 is some constant number. X is independent variable and the operator corresponding to momentum, as we have discussed, p cap is equal to minus ih cross partial differentiation with respect to x. Now when you operate p cap on psi, this will offer you minus ih cross del x of psi, that is minus ih cross del x. Psi is replaced by this e to the power I p0 x upon h cross. So if you find derivative with respect to x, it will be the function e to the power x, e to the power function into derivative of function f dash, that turns out to be simply p0 psi. Here the state is represented by psi and the momentum by eigenvalue p0 is real. Now let us talk about the position eigenstate. Let q cap is an operator corresponding to position eigenstate. Q cap operated on psi offers x psi, where x is the eigenvalue. This x is not equal to a because the location changes. Therefore, the constant numerical value cannot be assigned to it. However, in earlier case where we were talking about the position eigenstate p0, we could have equated with a. p0 equal to a could have been possible, but here x equal to a is not permitted. In quantum mechanics, we talk about probability p between a and b. The probability of finding particle between a and b is integration from a to b psi star psi dx, where psi star psi represents probability density and its numerical value is independent of a, but it depends on b minus a. We'll see all values of coordinates are equally probable. That is, when the particle is in the momentum state p0, then there is no specific location to the particle. Its probability is equally spread everywhere. If the momentum is known, position is unknown. That is the argument. So here, if the momentum is known, position is unknown. The value of position coordinates by wave function psi is not predictable but can be measured physically. Thus, quantum mechanics says that when the momentum of the particle is known, its position has no physical reality. If we consider quantum mechanics is incomplete and described by a wave function psi, and the momentum is known, then the position is uncertain. So, if this is the situation, then how quantum mechanics is complete? This is the question posed by Einstein, Podolsky, and Rosen. In quantum mechanics, it is usually assumed that the wave function does contain complete description of physical reality of the system in the state to which it corresponds. At the first sight, this assumption is entirely reasonable for the information obtainable from psi, seems to correspond exactly to what can be measured altering the state of the system. We shall now show, however, that this assumption together with the criteria of relativity given here leads to the contradiction, and this is the EPR paradox. For an amateur reader, you may find mathematics quite sophisticated, so to unfold that, we shall warm up through Dirac delta function, shifting property, and representation of wave function for two particles, so that we can smoothly sail through the arguments made by Einstein, Podolsky, and Rosen. Let us first deal with the Dirac delta function. The Dirac delta function is a Gaussian distribution, a bell-shaped curve squeezed so tight that it becomes perfect spike with infinitesimal standard deviation sigma. It is expressed as appearing on your screen del of x equal to sigma tending to 0 1 upon under root 2 pi into sigma exponential of minus x square upon twice sigma square. Here we are dividing by under root of 2 pi into sigma offers the function normalized such that the area under the curve is unity even though we go to infinitely sharp limit. Del of x is equal to infinity if x is equal to 0 and del of x is equal to 0 if x is not equal to 0. In both the situations, integration from minus infinity to infinity del of x dx is unity. The use of del x is a common and convenient and easy way to describe a perfectly localized distribution. Now we are into a Maple worksheet wherein I have just entered this function which we have discussed in the last slide. And the only thing is that I am going to enter plots interactive command, and in the bracket I have selected that function. So when we run this, it offers two kinds of plot. First of all, I shall plot interactive plot with one parameter. X I shall roll from minus 2 to 2, whereas sigma I shall roll from 0 to 0.2. For example, I can generate a return plot command. So this command I want to explore for plotting, and here you can see sigma is at the middle value 0.1. If you go on reducing this sigma, the sharpness of this belly curve grows up, whereas if sigma is increased, the belly shape shows a different shape, elongated shape, rather horizontally stretched kind of slope. Howsoever, all the time, area under the curve is maintained unity. So when we are going closer to 0, that time your y-axis is raising to maintain the same area under the curve, that is unity on the given scale. Now we shall again run this same command, plots interactive, and this time I want to roll the whole stuff for animation. So here I am selecting animation. X I am selecting again from -2 to +2, sigma 0 to 0.2, and I shall ask for the command, and it has returned me command, and I am executing this command. So selecting this, we can run the animation. In practice, reality is never perfectly sharp, but we can use del x in arguments where small blurriness is irrelevant. You can always replace del of x with a very tight Gaussian if you'd like. Don't take the infinity and infinitesimal things too literally. EPR paradox does not depend upon perfect sharpness of delta function. The next point of discussion is shifting property. The Dirac delta function picks out or shifts the value of a function at a specific point, say x equal to a. Everywhere else, this function del of x minus a is 0. So only the value of the function at x equal to a contributes. So del of x minus a is 0 everywhere except x equal to a. Now think of del of x minus a as a mathematical needle. It is 0 everywhere and infinitely sharp at x equal to a. Don't take it literally infinitely sharp, because the area under the curve has to be unity, and I am splitting this integral over limits from minus infinity to plus infinity. This is split over minus infinity to a, then a to a, this is little weird, and then a to plus infinity. So everywhere else it is 0. So here you can observe 0, and it is infinitely large at x equal to a. So when multiplied by f of x, it extracts only f of a. The integral can't depend on function evaluated everywhere other than x equal to a. So del is an intermediate concept which washes away the story elsewhere and yields the value of the function at x equal to a. That is the concept. Now shifting property or picking up property we shall understand for one particular function where f of x is equal to x square. Then del of x minus a into f of x, in this particular case we shall consider for del of x minus 2, where the value of a we have substituted 2 and the function is replaced by x square. Now for this situation, by definition, del of x minus 2 we can write limit sigma approaching to 0 from positive side 1 upon 2 under root of 2 pi into sigma e to the power minus x minus 2 whole square upon twice sigma square into this x square. So actually this del function I have replaced by its actual function that we have used in the earlier slide. Now we can take this limit outside and constants outside, and we can evaluate this function, and incidentally it turns to be equal to 4, which is actually f of 2, that is equal to 2 square. Now one has to solve this integration, that's the matter. And this looks to be a little complicated equation, so I am going to take you into Maple worksheet to solve this out so that you develop a complete feeling of what is going on. So in physics, del of x minus a or del of x minus 2 as we have considered represents a point source or impulse. The shifting property means a system responds only at exact point where the impulse is applied. For example, we experience point charge, impulse, force, localized energy input, and so on. So here we are again into the Maple worksheet where we are interested in finding del of x minus a, that is del of x minus 2. So here a is 2. So function will appear like this. Sigma we shall substitute close to 0, say 0.01, and we shall plot f2 for the range from minus 2 to 4. In this range you can see the sharp peak at x equal to 2, x equal to a is equal to 2, and at that point we get a sharp peak, and this is because of the pre-exponential factor 1 upon under root of 2 pi into sigma exponential of minus x minus a square upon twice sigma square. We are now in position to discuss shifting property. For discussing this, I am raising f1 as we have done in the earlier slide, and that is equal to 1 upon under root of 2 pi sigma exponential of minus x minus 2 whole square upon twice sigma square. And g, we shall define a function that is to be integrated is x square times f1. So x square is a basic function, and f1 we have already discussed, and we shall substitute sigma close to 0. For example, say 0.2 value we shall pick up for sigma, later on we'll reduce it, and then we shall integrate this last function f over x ranging from minus infinity to plus infinity, and we obtain value 4.04. It is close to 4. Now, if you choose sigma quite close to 0, in that situation, the value of 4 will be more close to 0, and if you choose sigma very small, then it will be very close to 4. Actually, it is f of a, and a square, a is equal to 2, so that results into what you call value very close to 4. Now we shall talk about expansion of wave function. Any wave function psi can be expressed as a linear combination of eigenfunctions of an operator, especially a Hamiltonian operator. Because eigenfunctions of a Hermitian operator form a complete and orthogonal set. The physical meaning of this states that each eigenstate represents a definite measurable value. For example, energy. The coefficients mod of an square gives the probability of measuring eigenvalue. So expanding the wave function psi of x as a superposition of discrete eigenstates un with an expansion coefficient an for some observable, say capital A. The eigenstates of observable comprises of a complete orthonormal set. So we can write the same thing as sum over eigenstates Vn with coefficient Bn. And that's the sort of one of the main rules that you learn when you learn quantum physics is that if you have an observable quantity and that's going to have a set of eigenstates corresponding to the set of eigenvalues that are the measurable quantities for that observable, then those eigenstates give you a set of basis functions with which you can construct more arbitrary wave functions. by superimposing a bunch of those different eigenstates. And here, by orthonormal, what I mean is that if you take two different eigenstates and take their inner product, you get 0. So they are sort of perpendicular in that sense. They don't get in each other's way, but they are also normalized. So if you take the inner product of any eigenstate with itself, you get number 1 corresponding to a normalized wave function. We can write those two conditions in one equation by showing integral form of the inner product between two states and showing that equals delta sub nm, where this is a Kronecker delta which takes value 1 when n is equal to m and takes on a value 0 when n is not equal to m. Now consider the case of quantum harmonic oscillator. In that situation, we have eigenstate un expressed as appearing on your screen, where L stands for under root of h cross upon n omega and zeta stands for x by L. En, that is the energy of nth state, is equal to h cross omega inside bracket n plus 1 by 2. If you are not knowing quantum harmonic oscillator, it does not matter, but this is the way a sample expression for eigenstate is we have worked with. So in the left half you can see the animation of quantum harmonic oscillator, and in the right half you can see a wave function representation of first 8 bound eigenstates for n ranging from 0 to 7, E0, E1, E2 up to E7. So these are the 8 bound eigenstates, whereas the horizontal axis shows position. Corresponding to probability density, the coherent state dynamics for given numerical value of alpha equal to under root 10 in the units of harmonic oscillator length x0, which is equal to under root of h cross upon m omega, showing the probability density mod of psi square. Now here in this animation you can see mod of psi square on y-axis, whereas x upon x0 on x-axis, and quantum phase, that is argument of psi, you can identify with the colors. So the corresponding wave function psi for first, second, third and so on and so forth nth bound state can be expressed like this, whereas the energy En, we have h cross into omega into n plus 1 by 2, and psi can be expressed in this fashion, wherein An can be found using integration from minus infinity to plus infinity, un star, that is complex conjugate of un, into un itself dx, whereas the summation of mod an square for all values of n ranging from 0 to infinity should amount to unity to normalize the probability, and thus wave function, which is not only function of position but also time, can be expressed as summation n rolling from 0 to infinity an un into e to the power I h cross en t. This very illustration depicts two quantum particles located in separate light cones, suggesting they are causally disconnected in space-time, meaning no signal traveling at or below the speed of light can pass between them. Each particle sits at the center of a cone-shaped space-time structure. The blue cone on left-hand side and the orange cone on right side represents distinct regions of space-time, past and future. The particles appear isolated in their respective regions, emphasizing relativistic separation. Despite this, a glowing wavy connection links them, symbolizing quantum entanglement. This highlights the key idea which we are talking about here. Even when particles are separated beyond causal connect, their quantum states remain correlated. A measurement on one instantaneously influences the state of the other, reflecting the non-local nature of entanglement. Overall, the diagram visually contrasts relativity as well quantum mechanics. In relativity, we are contrasting with light cones and causal limits. In quantum mechanics, entanglement and non-local correlations. It's a conceptual representation of how entangled particles challenge classical notions of space-time and causality. Now that we want to represent a wave function for two entangled particles. A simple way to represent two entangled particles, each localized in the different light cone regions, separated by impassable barrier, is to write a tensor product state that combines their spatial separation with an entangled internal degree of freedom like spin. A standard example is a Bell state with spatial localization. The wave function psi can be represented as appearing on your screen, where psi A represents a wave packet localized in one light cone, say blue, and psi B in another light cone with spin up and down states in the usual bracket notations. Here I want to emphasize on the key features that particles are spatially separated and psi A and psi B are totally independent, having negligible overlap or no overlap. The state is non-factorizable, so that you cannot write psi equal to product of psi 1 and psi 2 or psi A and psi B, for example. The measurement of one particle determines the state of other anticorrelation, and in compact notation we can represent psi like this. Now in the last slide we have developed a wave equation, a combined wave equation for two particles, two entangled particles. In the silent depths of quantum world there existed a tiny region where the energy briefly fluctuated. From this fleeting moment, two particles were born together like twins sharing a single breath of existence. They were not ordinary particles. From the very instant of their creation, they were bound by an invisible connection described by the strange rules of quantum mechanics and quantum entanglement. So this equation we have already established in the previous slide, which is a wave equation for a pair of particles, entangled particles. The first particle I'm talking about, mod of psi x1 square, represents the probability density, and probability of finding that particle at x1 is capital P of x1 over the real space, integration over real space mod of psi 1 square dx. In the similar fashion, for the second particle, mod of psi of x1 x2 square represents the probability density. That is, the probabilities of finding first particle at x1 and second particle at x2 can be expressed by p of x1, which is a real coordinate, real number from real analysis, and x2 is the position of second particle, which is having a real coordinate. This probability of finding first particle at x1 and second particle at x2 is double integration over R1 cross R2. That is the spectrum bound by two real systems. This integration is operated on integrand mod of psi x1 x2 square, and this integration is operated over dx1 and dx2. Now, EPR makes a sharp argument with an idealized state psi of x1 x2 where the two particles have perfectly anticorrelated momentum. Thereby, P2 is exactly equal to minus of P1. So we are using the word anticorrelated, and perfectly correlated position, which is x2 equal to x1 plus x0. I'm just carrying forward the last equation, and here Einstein-Podolsky Rosen paradox also applies to more general, messy, realistic states, but the argument is stated most clearly for idealized wave function psi. And this function I am rearranging in two parts, exponential of I upon h cross p into x1 as the first part as it is, and in the second part minus is taken common and it will be x2 minus x0 multiplied by minus I upon h cross p. So here what we have done, collapsing psi of x1 x2 into two momentum eigenstates, up of x1 and psi p of x2. Here if you clearly observe, then you can see integration has gone away and we have only integrand. Upx1 is a momentum eigenstate with eigenvalue p as expected, but psi p of x2 is also a momentum eigenstate with eigenvalue minus p. Here you can observe this is the minus sign associated with p for particle 2. Measure momentum of particle 1 and psi collapses into two momentum eigenstates, one with p for particle 1 and other with minus p for particle 2, anticorrelated. Psi of x1 x2 appears as sum over particle 1's momentum eigenstate with expansion coefficient that the function of particle 2's coordinate. So we measure the momentum of particle 1 and project psi into a specific momentum eigenstate up of x1 with specific momentum p. You are collapsing momentum of specific eigenstate that makes the last equation. Now here we are going to talk about another form of the wave function wherein I am introducing alpha to replace x1 minus x2 plus x0. So in this last equation we are replacing this bracket by alpha and we obtained this expression. And I am representing the same thing wherein I have introduced exponential of minus epsilon p square, epsilon tending to 0 into the same function exponential of I upon h cross p alpha. This I have borrowed here. So this looks like Kronecker delta in Gaussian form. and collectively I can write a common exponential function of minus epsilon p square plus I upon h cross p alpha. In the next slide, I am going to just consider the exponent and I'll tackle that only, and we'll get back to this psi of x1, x2. Now in this last equation, consider only exponent minus epsilon p square plus I upon h cross p alpha. Take minus epsilon common inside bracket, it will be p square. Instead of this plus, it will be minus, and there will be one epsilon in the denominator. So I upon epsilon h cross p alpha. Now we are going to do some mathematical adjustment, as we are multiplying by 2 and dividing by 2 so that it remains as it is. Then we are adding this term I alpha upon twice epsilon h cross square and minus same quantity I alpha upon twice epsilon h cross square. So this adjustment we are doing with specific purpose, and that purpose you will understand. We want to make out a square, x square minus twice x y plus y square. So this will be minus epsilon common as it is here. So this minus epsilon is common, and minus p minus I alpha upon twice epsilon h cross whole square minus I alpha upon twice epsilon h cross square. So here we can clearly write minus epsilon times p minus I alpha upon twice epsilon h cross whole square minus, so what we are doing here, this minus has come here, so minus minus plus, and I square has taken it to minus, so alpha square upon 4 epsilon, 1 epsilon is cancelled, and h cross square as it is. So here we have obtained the requisite form. Now this psi equal to equation we are handling since last 2-3 slides, and exponent I am writing minus epsilon p square is equal to I upon h cross p alpha. This we have written like this. Why we have done this? Because the exponent is quadratic in p square and it is linear in p. So this complexity we want to resolve, so we have adjusted the terms in this fashion. And now I am going to substitute p minus I upon alpha twice epsilon h cross is equal to q, and dp we are replacing by dq. So here dp we shall replace by dq, and here this bracket we shall consider alpha. Now by that substitution, and we are carrying out this minus alpha square upon 4 epsilon h cross being constant out of integration sign. So we are left with this integration minus infinity to plus infinity exponential of minus epsilon q square dq. This can be fitted in the standard format of integration, which is under root pi upon a. So it will be under root pi upon epsilon. So this is how we have simplified psi of x1, x2 in this fashion. Now here I am carrying forward the last equation that we have dealt in the earlier slide, and here I want to locate the Dirac delta function. It is of the form del of alpha equal to limit sigma approaching to 0 1 upon under root 2 pi into sigma exponential of minus alpha square upon twice sigma square. Now here I want to locate everything. For that purpose, I shall compare this 2 sigma square with 4 epsilon h cross square, and I'll simplify sigma, that is equal to under root of twice epsilon into h cross. One thing. Another thing is that 1 upon under root of 2 pi sigma is appearing over here as a pre-exponential factor, and here the pre-exponential factor is under root pi upon epsilon. Now actually I want to settle this part with this part. So 1 upon under root of 2 pi into sigma, where sigma is under root twice epsilon h cross. So I am substituting here. So here you can observe that under root 2 into under root 2 is 2. We are left with under root of pi into epsilon, and outside under root we have h cross. So I want to locate this quantity under root pi upon epsilon, and the remaining part is 1 upon 2 pi h cross. Actually, our psi function of x1, x2 will be 2 pi h cross times del of alpha, because this factor you need to multiply by so that you can get del of alpha, where sigma has this meaning, and h cross is h upon 2 pi. So 2 pi h cross I can simply write as h del alpha, where alpha we have x1 minus x2 plus x0. So I'm carrying forward this equation in the next slide. In this slide, we are going to explore shifting property for the wave function. Now, shifting property states that integration from minus infinity to plus infinity, Dirac delta function del of x minus a into f of x dx is equal to f of a. Now this Dirac delta function will vanish everywhere except x equal to a, and at x equal to a, this function has this integration after solving has value f of a. This we have established with an example. In the reverse version, I want to use it for our purpose. This was our last equation in the previous slide, where we are interested in exploring h into del of x1 minus x2 plus x0. Now, I am insisting on the point that we are talking about exploring this as f of a. Therefore, I am saying that inverted version of shifting property. This function is this del, and Dirac delta is this one. Now, h into del of x1 minus x2 plus x0 is equal to integration from minus infinity to plus infinity h as it is, and this is our Dirac delta function del of x1 minus x. This will vanish everywhere except x equal to x1, and the moment you substitute x equal to x1 here, the integration leads to this del of x1 minus x2 plus x0, which is actually f of a. So this is actually f of a. Function is del of x1 minus x2 plus x0, and the Dirac delta function is this part. I hope I am quite clear with this. However, in the beginning, before starting this another form, we have established that psi of x1, x2 is equal to integration from minus infinity to plus infinity, exponential of I upon h cross, p into x1 minus x2 plus x0 integrated over momentum dp. So now these two things are equal. I mean to say that this is equal to this, which is our another form of wave function. We have wave function represented in these two fashions. One is our position and another is our momentum. Instead of measuring momentum, let us measure position of the particle 1. For this, we want to express wave function as an integral over the position eigenstates of particle 1. Here, we mathematically mean that del of x1 minus x is represented by Vx of x1 and h times del of x minus x2 plus x0 is represented by phi x of x2. Phi x of x2 is position eigenstates of particle 2 with positive eigenvalue x plus x0. So I want to highlight the eigenvalue, that is x plus x0. So I am talking about this x plus x0, and in the another case we have eigenvalue x. Now we have phi x equal to h. This already I have explained you. If we measure the position of particle 1, we collapse the wave function of particle 2 down into the position eigenstate. The position of particles are perfectly correlated with x1 and x2 separated by distance x0 at the same moment of time. Thus, depending on whether we measure momentum or position of particle 1, we put particle 2 into momentum or position eigenstate. Wouldn't that mean particle has to have both real momentum and position? And wouldn't that mean quantum mechanics is incomplete? So by now we have taken a long ride into mathematics to establish this equation wherein psi of x1, x2 is integration from minus infinity to plus infinity over dp e to the power I upon h cross p alpha. This is alpha, and this was broken into these two pieces wherein we have h into del of x minus x2 plus x0 being replaced by phi of x at x2. So this x2 is important, and then v of x at x1 by this del of x1 minus x. And here we have explicitly written that by this we collapse the wave function psi x1 x2 of particle to down into the position eigenstate. When we measure position of particle 1, the position of particles are perfectly correlated with x1 and x2 separated by distance x0 at the same time. So the position eigenstate of Vx having eigenvalue x at the particle 1 and position eigenstate phi x is having eigenvalue x plus x0 for particle 2. Depending on whether we measure momentum or position of particle 1, we put particle 2 into momentum or position eigenstate respectively. So after all, I want to develop a review of what we have discussed, and here you can observe Vx of x1 and phi x of x2 and up of x1 and phi p of x2. And here when we measure position of particle 1, the position eigenstate of Vx1 is del of x1 minus x, that is Dirac delta function expresses that, and the corresponding eigenvalue of the eigenstate Vx of x1 at P1 is x. P2. For particle 2, the wave function collapses into position eigenstate described by phi x of x2, which is expressed by the Dirac delta function del of x minus x2 plus x0. This has eigenvalue x plus x0. And if we try to measure momentum of particle 1, then the momentum eigenstate is expressed by up of x1 e to the power I upon h cross px1. This offers momentum eigenvalue p, and P2 collapses into the eigenstate. The wave function for particle 2 collapses into the eigenstate having eigenvalue minus p, perfectly anticorrelated. In this paper written by Einstein, Podolsky and Rosen, a famous thought experiment is discussed which is designed to question whether the quantum mechanics provides a complete description of reality or not. I am going to read a paragraph from his paper. For this purpose, let us suppose that we have two systems, 1 and 2, which we permit to interact from the time t equal to 0 to t equal to capital T, after which time we suppose that there is no longer any interaction between two parts. We suppose further that the states of the two systems before t equal to 0 were known. We can then calculate with the help of Schrodinger's equation the state of the combined system 1 plus 2 at any subsequent time, in particular for any t greater than capital T. Let us designate the corresponding wave function by psi. We cannot, however, calculate the state in which either one of the two systems is left after the interaction. This, according to quantum mechanics, can be done only with the help of further measurements by a process known as reduction of wave packet. Now, let us consider the essential components of that. We have psi of x1, x2 expressed as summation n rolling from 1 to infinity psi n. This is a coefficient depending on x2 into eigenstate up depending on the first variable x1. A physical quantity A corresponding to system 1 we are trying to handle. The physical quantity A corresponding to system 1 possesses eigenvalues A1, A2, A3 and so on corresponding to the eigenfunctions U1 function of x1, U2 function of x2, U3 function of x3 and so on and so forth, where x1 stands for the variable of system 1. On contrary, x2 stands for the variable used to describe system 2. Here, psi n of x2 are merely coefficients corresponding to the expansion of psi x1, x2 into a series of orthogonal functions of up or uk or sometime un. Suppose the quantity A is measured and is found that it has eigenvalue ak. It can be concluded that the measurement of the system 1 is left in the state given by the wave function psi k x2. Therefore, the series psi n x2 and up x1 reduces only to this psi k x2 into uk x1, which is equal to ak uk. You can observe here ak uk, which is the only existing term out of that, because these all terms are becoming zero, and therefore we are left with this very output ak uk function of x1. Now here we shall discuss the physical quantity B corresponding to the system 1 psi function of x1 x2, two particle system, can be expressed together as summation phi s vs. Let us choose another physical quantity B having eigenvalues b1, b2, b3, so on and so forth, and the eigenfunctions v1, v2, v3, so on and so forth. Phi s function of x2 are new coefficients of vs that are depending upon position. If the quantity B is measured and found to have a value BR, we conclude that after measurement, the system 1 is left into the state given by Vs function of x1, and the second system is left into the state given by phi r x2. So we collapse particle 1 into uk function of x1, and particle p2 becomes psi k x2. So this is a collapse we are causing of the wave function, and similarly we collapse particle 2 into ur function of x1, and the particle 2 becomes phi r function of x2. So we have two wave functions which are highlighted on your screen. Psi1 depending upon x1 and x2 expressed as summation of product of psi n un, where psi n is function of x2, un is function of x1. Similarly, product phi s x2 into vs x1 for the same reality. As a consequence of two different measurements performed on system 1, left the system 2 in the state with two different eigenfunctions psi k and phi r, both functions of x2. On the other hand, since the time of measurement of two systems no longer interacts, no real change can take place in second system in consequence of anything that may be done in system 1. Thus, it is possible to assign two different wave functions psi k and phi r for the same reality prevailing. What is this? I mean, this is absurd. This is a problem of quantum mechanics. Wave function collapses. Wave function collapse is non-local. We are revisiting this slide. Previously, we proved that either number 1, quantum mechanical description of reality given by the wave function is not complete, or second, when the operators correspond to two physical quantities do not commute, these two quantities cannot have simultaneous reality. Starting then with the assumption that the wave function does give a complete description of reality, we arrive at a conclusion that the two physical quantities with non-commuting operators can have simultaneous reality. The negation of one leads to negation of the only other alternative of two. We are thus forced to conclude that quantum mechanical description of physical reality given by a wave function is not complete. One could object this conclusion on the grounds that our criteria of reality is not sufficiently restrictive. Indeed, one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous element of reality only when they can be simultaneously measured or predicted. On this point of view, since either one or the other, but not both simultaneously, of the quantities P and Q can be predicted, they are not simultaneously real. This mix of reality of P and Q depends only on the process of measurement carried out on the first system, which does not disturb the second in any way which could violate our local causality. With this much, we will conclude our video. I recommend you to go through the original paper once. Thank you very much.